Okay, we're being recorded, so we need to behave a little bit. So it's a pleasure to have Jan Špakula here. He's going to be talking about quasi-locality. And that's it. Please, you have the floor. Go for it.
Thank you very much. Thank you for the invitation. In terms of sort of etiquette, I mean, feel free to interrupt anytime you have a comment or a question, which hopefully there will be some. And also, I've prepared probably too much stuff. So we'll get there. So what's the plan? Let's see. So here's the plan. So I'm hoping to get through first three things, and then the rest is going to be sort of choose bits. Right. So I want to just sort of very briefly say something about coarse geometry and define what the row algebras are, then explain what quasi-locality is, and then talk about the results. And then the results too are the more recent ones, which then connect with the rigidity results. And then the 4 and 5 are sort of towards proofs. So 4 is explaining what property A is, which makes an appearance before, but I'm not going to say anything about it then. And then sketches of proofs are sort of sketches of proofs for the first set of results, which you'll see. So, right. So, coarse geometry. Right. So the slogan there is, let's see who. Okay, we've probably all heard this at some point. So but anyway, let's go through this. So coarse geometry is a part of metric geometry. So no function analysis at all as such. And the idea is supposed to be to study metric spaces from a large scale perspective. And sort of the group theoretic take started with Gromov and the kind of the function analytic applications or connections with John Roe in the, I guess, late 80s, early 90s. And instead of trying to explain any more about this, let me just give you the definition of coarse embedding and coarse equivalence. So this is supposed to be from large scale perspective, when do you say that the spaces are the same in large scale? And that's the notion of coarse equivalence here. So let me read the definition and then try to explain and then go through some examples. So X and Y, capital X and Y here are metric spaces. And I'm going to say that f, a function from X to Y, is a coarse embedding if the following condition holds. So if there exist two functions from interval 0 to infinity to itself, rho plus and rho minus, I'm requiring, the only requirement really is that rho minus goes to infinity eventually. And they should satisfy the following things. So for any 2 points X and Y in X, they're supposed to tell me how much does my F distort the metric potentially, right? So it compares the distance in the target with the distance in the original space in X. And there is a lower control function rho minus and upper control function rho plus. So this is like super flexible, right? I mean, they can be, rho minus can go to infinity very slowly, rho plus can go, super exponentially. And then that means that the distortion can be pretty much anything. Right, so that's a coarse embedding. And to make it into coarse equivalence, you kind of require that you hit almost everything in Y. And the coarse condition is this one. So if you look at everything that's hit, you want that everything else is at most bounded distance from it, right? So there is a universal constant so that if you look at any point in Y, there is something in the image within that distance close to it. So that's a coarse equivalence. Now it's defined one way, but it is actually an equivalence. So if there is a coarse equivalence one way, there is also the other way. So it is really like an equivalence relation sort of on the metric spaces. And again, just like with topology and all that, there is a more general notion. You don't have to talk about metric spaces, but I mean, if it's the first time you see this, then you should just really think metric spaces. There is an abstract notion of a coarse structure, which is more general than a metric space, but the metric space is a good start. So yeah. Right. Oh yeah. So apparently, I mean, it deletes my notes, but that's fine. So examples. So I guess the first one is that this is so flexible that any bounded space is coarsely equivalent to a point, right? So this is the opposite of topology, where you care about sort of small things, neighborhoods and things. In coarse geometry, any bounded thing is the same thing as a point. So you can't ignore this. Now, it does, so the coarse equivalence looks super flexible, but it's not that flexible that it washes out everything, right? So an example of this is that if you take the integer lattice z to the n, so dimension n, and the integer lattice dimension m, with the natural metric that you would have on these things, they happen to be coarsely equivalent if and only if the dimensions are the same, right? So somehow that some notion of dimension which gives you n for Zn survives this coarse equivalence. And then finally, all the spaces I've talked about so far were sort of discrete, but I mean, there is no requirement for anything to be discrete. But in the coarse sense, you can always make things discrete if you want to, up to coarse equivalence, right? So the first example of this is that Rn, the Euclidean space, is coarsely equivalent to Zn, the lattice, with whichever metric you put on this. I mean, they're all going to be coarsely equivalent. And somehow you can generalize this to like a setting where, I mean, if you take any, say, this other thing, so the more general version of this is the Schwarz-Milner lemma. So if you take a universal cover of a compact manifold, then it's going to be coarsely equivalent to the fundamental group of the manifold, right? So the fundamental group of manifold is sort of, you think of this as a discrete object, which sort of sits as an orbit inside this universal cover. And the universal cover is a manifold, so it's pretty nice, continuous and all that. But you can always, in coarse sense, you can replace it just by talking about the fundamental group. Right, going pretty slow. So yeah, let's skip the last bit. So that's the connection to group theory. And now let's just talk a little bit about why people talk about this. It seems sort of, yeah, why? Well, the point is, for both of these people who kind of initiated these things, so Gromov and John Roe, that's sort of the common thread, which then, you know, you plug it into some function analysis machine, and it gives you sort of strong theorems in various other fields, like in geometry, where you can use this machinery. I mean, you coarse geometry, plug it into Roe algebras, do some other stuff. You get results about non-existence of metrics of positive scalar curvature on manifolds. And the famous topology application is the Novikov conjecture, which I couldn't actually state for you if you asked me. Sorry. For me, it's a black box, but yeah. Okay, so okay, so what's this function analytic thing? Oh yeah, before we get there, let me list pretty much all the coarse geometric properties that exist right now, and they are all nicely ordered, more or less. I mean, some of them have different names, but this is kind of it, this picture. So so these are, I mean, when I talk about, I mean, some of them will come up later on when I talk about results, where I have to assume some coarse geometric thing about the space. Some of them don't, but just so that you have a picture. So there's this notion of asymptotic dimension, which say Zn has dimension n, even the asymptotic dimension n. Then there's a more general notion of finite decomposition complexity. And then the more general notion is property A. And that's the one which has many different formulations. So these kind of various weird looking abbreviations are all just that, turned out eventually. Then the more general thing is coarse embeddability into L2. So at least this one, you can imagine. I defined what the coarse embedding is. And you can ask, if given a space, whether you can actually coarsely embed it into little L2 or capital L2 if you want. I mean, that's equivalent. Right, so it may be possible or may not. And it turns out that that's one of the properties that's relatively important in this business. And you can think of this as sort of on the large scale, trying to draw your space in an Euclidean space, infinite dimensional one. And then there is a little more general one, which is coarse embeddability into little LP, where P is greater than 2. For P less than 2, it's the equivalent to the previous thing, but yeah. And then, right, so those are, you should think of these as sort of levels of niceness, right? So things with finite asymptotic dimension, super nice. And then you go on, property A is still sort of workable. You can prove things about it with it. Then it gets really much harder with coarse embeddability usually. And then, so here be dragons means that that's a, a class of spaces which do not coarsely embed into any LP. And that's the one where we don't really have that many sources of examples, and that's where weird stuff happens, as you will see, I guess, in this talk later on. Right. So let's go to row algebras. Right. So my X throughout the rest of the talk will be a discrete metric space with bounded geometry. By bounded geometry, I mean this condition that if I fix a radius and I look at all the balls with radius r and count how many points are in those balls, I should, that number should be uniformly bounded from above, regardless of X. So that's what bounded geometry means. And again, if it's the first time you see these things, you should think of Z with the normal metric, like absolute value, or Zn, or this sort of thing, which becomes important later on. So let me go through this. So you can, let's start with a sequence of finite graphs. Let's denote them by Gn. Let's say connected, just to avoid things. On each Gn, I mean, when I say graph, I really just mean the vertex set, right? I want the discrete metric spaces. I think of vertices as my space. And I endow it with the path metric. So the shortest path, right? In a graph, the length of the shortest path between 2 points, that gives me a metric on the set of vertices. That's my finite space Gn. Now I have a whole bunch of them, and I can kind of stick them together into a single space by doing this coarse disjoint union operation. So you should think of this as, you know, start sticking G1 and then G2 and then somewhere else G3. Think of them as growing in size, and also think of the distances between them being larger and larger, right? So that in the end, I can, I mean, up to coarse equivalence, there is a single metric which does this. And so that's going to be my coarse disjoint union. So that's an infinite space now, from build up from finite pieces. And that's this sort of thing is going to, again, make an appearance. So yeah. So again, think of X equals Z and X equals this kind of gadget where, yeah. Okay. So we will work on LP or L2 of X. And I mean, this is silly in this kind of seminar. So we think of operators on L2 or LP as matrices with entries, well, here in complex numbers. And yeah, so this is just how it works, right? So this is my vector in LP. That's my operator T, I mean, represented as a matrix, and that's the result. So yeah, there's nothing important here. Oh, well, nothing deep in that slide. So here we define row algebras. So, I mean, it's what's a row algebra? So your output or your input is a discrete metric space with bounded geometry, so X, and the output is supposed to be some operator algebra, usually sister algebra, but you know, there are Banach algebraic versions of this now. And they are supposed to somehow encode coarse geometry of X. So I'll get to this point, how do they encode coarse geometry, but let's first go through the definition. So again, I work on LPX. If I take an operator, now again represented by a matrix, it is said to have finite propagation or be a band operator if there exists R, so that whenever, if I take 2 points, distance at least R, then that corresponding matrix entry is 0. So pictorially it's here. So this is my matrix of an operator, and I basically require that the only non-zero entries are in this band along the diagonal, so somewhere here. Right. So hence band operator. Right. So if I take the collection of all of these things, they form an algebra in B of LPX. If it's L2, then it's a star algebra. But of course, it's not closed unless X is finite. So we close it in norm to get an operator algebra. So I'm going to denote them. I mean, if I talk about the P version, I'm going to denote them BP. So the norm closures of these finite propagation operators. But the more traditional notation for the sister algebraic version, so for L2 version, is this C star sub U of X. This sub U stands for uniform. Right. And I mean, if there's any operator theory people here which look at these things, then you probably know the name band dominated operators. So those are norm limits of band operators. So in other words, members of these operator algebras defined over there. Right. So, I mean, metric makes an appearance in the definition. So presumably it's somehow reflected in the sister algebra or in the Banach algebra. So how? Well, right. So here's the demonstration of this kind of connection to coarse geometry. Turns out if two spaces are x and y are coarsely equivalent, then the corresponding operator algebras are, well, not quite isomorphic, but they are at least stably isomorphic. So if you tensor with compacts, they become isomorphic. Right. Okay, so at least one way it works. So it is a kind of the operator algebras or their Kerr theory is sort of a coarse invariant. So it's a thing which depends only on the coarse geometry of the space. You can ask whether you can kind of go back. So how well do these things encode coarse geometry of the underlying space? So here's a sample theorem. Right, so that's a question which has not been sort of fully understood or answered. So there are only partial answers, which are generally positive. And they go like this. So you assume something about the space, that it's reasonably nice. So if you remember my hierarchy of coarse properties, it's kind of in the middle there. So say if X is property A, then isomorphism of the algebras does imply coarse equivalence of the underlying spaces, right? So I'll come back to these things. These are so-called rigidity results. So this is a sample, one of those. Right. So that was about Roe algebras and coarse geometry. Any questions so far? Okay. Right. Right. Okay. So again, this is another one which is not deep at all, but I wanted to put it there just sort of to make things sort of clear. So I think of my operators on L2 or LPX as sort of huge matrices, and I want to kind of cut them up, right? So just consider some portions of the matrix in a sense. And so the standard way to do this is to do things like that. So what are those things like that? So here's an example. If X is just 8 points, 1 to 8, you can think of it as with the normal distance if you like. And I take two subsets A and B. And I take any T in an LP of X, which is now 8 by 8 matrix. Here is how it works, right? So if I take if I take a subset of my X, I consider a characteristic function of that set as a multiplication operator on LP or L2. And now if I do something like that, so if I multiply by characteristic functions on left and right, it will exactly cut out a piece of the matrix for me, right? So if you imagine how multiplication works, if I take T, any 8-bind matrix, and I do this chi-A, T, chi-B, so characteristic functions from both sides, it cuts out just this piece of the matrix and zeroes out everything else. So, you are going to see the expressions like this a lot, and you should think of them as sort of just looking at as a portion of a matrix. Okay, so defining quasi-locality. So first, let me reformulate finite propagation with these cutting out portions of a matrix. So an operator T has finite propagation if and only if the following thing holds. So if there exists an R, so that if I take any subsets A and B of X, which are distance at least R apart, meaning that the distance between two sets is just infimum of the distances of all pairs of points, one from there, one from there, right? So two subsets A and B at least R apart. If I cut down T by those two things, I should get 0, literally, right? So if you think about how the cutting down works, that's precisely the condition. So if it's supported on a band, then if I cut out a piece which is at least R apart from the diagonal, then I should get the 0 operator, right? That's finite propagation. Right, now, okay, so let's cook up a property which will work for norm limits now. So let's relax this a bit and just do it up to epsilon, right? So the condition now that I'm just stating now for so far is that, let's say there exists an R, so that whenever I take two sets which are R apart, so that part is the same, I don't require that the operator is 0, I just require that the cut down has norm less than epsilon, right? And I can, the full condition is that for all epsilon, there should exist an R such that this happens, right? So you can imagine if you take any norm limit of finite propagation operators, it will satisfy this condition, right? Because simply you can always approximate up to epsilon over 2 to finite propagation guy, and then you get zeros literally as cut downs. And so cut downs of the original guy are going to be bounded in norm by epsilon. Right. And so we're just going to make it a definition. We say that an operator is quasi-local if that happens. And what I was just sort of blabbering about is that anything in any of these operator algebras, so row algebra, uniform row algebra, or the Banach algebra version of that, is going to satisfy these conditions. So, right. So one way it kind of works actually belongs to the corresponding, Banach algebra, so uniform row algebra. So that's a question. And so, I mean, the history is sort of strange. Well, I don't know if it's strange, but anyway, so John Roe pointed this out in his sort of 1996 CBMS notes in the book as a remark, right? So he said something like, oh yeah, so anything in the row algebra satisfies this condition. And now if the algebra, I mean, if the space is finite dimensional in the correct way, then also the other way around. And then we puzzled about the, I mean, I wanted to use this somewhere and I tried to figure out the proof and I couldn't at all. And so I think we spent some time with Rufus trying to figure this out and we also couldn't. So what was known then to John Roe is the following thing. So if the space X is actually Zn for some n, then it's true. So then any quasi-local operator does belong to the row algebra. And so this was done by the operator theory side of things. So by Rabinovich, Roch, and Silberman. And it somehow uses the fact that Zn is a commutative group, like pretty strongly. I mean, so we couldn't, I mean, I couldn't see a way of getting any further with this kind of argument. And then Alex Engel also proved, but much more recently, so, a couple of years back, that it also works when X has polynomial growth, whatever that means. I don't actually know the argument what he used. So yeah. But in any case, it took then like very, very smart sister algebra guy to figure out a trick to deal with this. But yeah, before I get there, so this is getting to the results. Why do we care about this at all? Well, I personally care because it was a question which I read as a graduate student, and it annoyed me. It seemed like a nice question. But I mean, there are some kind of conceptual reasons why this is good to know. So one is the first sentence is, if you want to show something is in the row algebra, so you construct some operator and you want to check if it's in the row algebra. Well, so far, the only way that you can do is to somehow use some procedure to figure out, approximants with finite propagation. So basically, literally by the definition, you just produce a sequence of finite propagation operators which approximate this. I mean, this is good enough in some cases, but not always, as was the motivation of Alex Engel here. And this condition of quasi-locality, it sort of gets away from this thing a little bit, right? You don't actually have to produce any approximants. You just need to check that if you cut down the operator away from the diagonal, you're getting small norm. So in a sense, that's kind of the motivation here. And this is literally, it can be used. I mean, Alex wanted to use it for these pseudo differential operators. So, index theory. So, I mean, even the name finite propagation comes from differential operators. So if you try to take the index of a differential operator literally, then you are getting sort of finite propagation things that in the construction. But if you try to generalize this to pseudo differential operators directly, you run into this problem that as the things that you do to construct the index, you actually kind of you are getting this condition, the quasi-locality, but you're not getting the finite propagation directly in any way. I mean, Alex found a way around this problem, so he didn't have to answer that question in the end. But I mean, it took some doing and a little bit of trickery. And then finally, it's used by Rufus and Stuart White in this recent work on uniqueness of Cartan subalgebras and row algebras. So I will not really say anything more about that unless you prompt me. Right. Any questions so far? Okay. So let's state a bunch of results about this. So they, well, actually two of them, and they both go in the direction of, okay, let's assume something out of the space, which will then imply that any quasi-local operator belongs to the Roe algebra, right? So that's the question that I was alluding to here. And this is the one that I would like to answer. I mean, both ways, but yeah. So we only have one way so far. So first result, so when I mentioned that it took a really, really smart guy in sister algebras to figure out what to do, that was A Tikuisis. So he came up with like a beautiful trick, which basically solves this thing in the case where the assumption of the space is this. You can kind of ignore what it actually says. It's one of the things I had on the list. Well, not exactly even. But yeah, anyway. Okay, so if X is a proper metric space and has this finite straight finite decomposition complexity, you know, I can't even say it. And we did it only in the Hilbert space case. So and P equals 2.
Sorry, just let me interrupt you just for a second. I always mistake those two. Which one is the strongest or the weakest? The straight finite decomposition complexity or finite decomposition complexity?
So the straight one is weaker than just the simple FDC, I think.
Okay.
Yes. So it has to do with, I don't really want to explain this very well. So, I mean, you should think of this as basically subtab version of finite asymptotic dimension, right? So if you know what that is, then you can sort of, I mean, that is sort of cutting up the space into a bunch of pieces in some nice way in one step. And this finite decomposition complexity soups this up by allowing you to not do this just one step and you cut the space in bunch of pieces in one way, but you do it sort of iteratively. So depending on some parameters. So you cut up the space into a bunch of pieces, which are not necessarily all finite yet. And then you ask again, and you cut those pieces in a uniform way into a whole bunch of smaller pieces, and you can repeat this finitely many times, right? So that's more or less what decomposition complexity is, finite. And the straight one, so the difference between the straight and the actual one is that in the actual one, the parameters you can choose after every step. And the straight one also asks only that, okay, I mean, at the beginning, I give you a list of parameters, and you need to produce these decompositions given that parameters up front. So that's, yeah, that's easier, right? So, I mean, but with this FDC, there, I'm not aware of any examples that would distinguish all these versions and even distinguish it from property A. So Rufus may know, but yeah, I don't.
No, it's open, I think.
Thanks.
Yeah. So, I mean, I guess a useful way to think about this is that it's sort of, well, if I get to the arguments, you'll see the difference, how things are used. So this is really kind of custom made so that you can cut up operators into pieces or some algebraic structures into pieces in some kind of finitely many steps, you get something. Whereas property A, which is the next theorem, is this kind of global requirement. So there's only a single thing, you get it for this whole space at once, and then you can use it. But it's weaker than being able to cut the space into pieces. So anyway, the next theorem, then I took needling of J Zhang. He just didn't, wouldn't let up and tried to talk to me about this. And so eventually we figured out, we generalized this a little bit to assuming property A, right? And all right, before that, Li, Wang, and Zhang generalized the argument of Aaron's to NEP. So that was a bit of work because, well, I mean, it's like the usual difference between sister algebras and just LP things. You lose the option to use positivity along the way, so that can be sometimes a lot of trouble. In this case, it was quite a bit of work, but I don't think it was sort of, terrible. And then, so the next theorem is the one where we assume property A for the space, and again, the same conclusion. So any quasi-local operator is in the Roe algebra. Right, and there's this special weird case. If P is either 1 or infinity, then you get everything for free. I mean, you don't have to assume anything about the space. So those are, you should, I mean, I think those are sort of weird cases when weird stuff happens. So
in the second theorem, are we still metric space, or is this a generic core structure?
Well, yeah, the metric space. Yes.
Okay.
Yeah, we didn't.
I guess we didn't define quasi-locality for core structures.
Yes, we did not. It's probably, yeah, that's a good question. I didn't actually think about this before. In a sense, you know, you should understand, I'm a lazy guy. I always think about metric spaces because it's just easier for me. But yeah, so yeah, we only did the sort of the I mean, really metric space with bounded geometry. So, I mean, the difference here is that this theorem is a bit more general because, again, at Aaron's prompting, I would never do this by myself. He wanted the result more general. So that's actually any proper metric space. So we do this, you know, not just matrices, but, you know, with these, yeah, I mean, the continuous version as well works in that argument. For our argument with GON, it's not, we didn't really try very hard, but that one uses some matrix kind of calculations. So I'm not sure. Well, maybe it does work, yes, but certainly no general core structures. Yeah. Okay, cheers. So in terms of consequences, there isn't really that much. Really just, you know, as you can tell, so for me, this is really a curiosity. But, you know, when you write a paper, you have to have something. So here's two. So one is that we can use this argument of the operator theory people, so Rabinovich, Roch, and Silberman, to prove that these LP versions of this uniform row algebra are closed under taking inverses. By which I mean, you know, if you have an operator which is in there and it's invertible as an operator on LP, then it actually, the inverse also belongs to BP, right? So that's for in the P equals 2 case, that's automatic because sister algebras, but with Banach algebras, it requires an argument, and we use this quasi-locality for that. So basically you can, yeah, anyway. That's relatively straightforward, right? So the thing is that this quasi-locality is more flexible. You can show that all kinds of things are quasi-local, like an inverse is a quasi-local thing. Whereas if you take an inverse of a finite propagation operator, you really know nothing about it in a sense. Yeah. So, all right, and along the way in the proof, we get another characterization of property A, as if there wasn't enough. It's very similar to this operator norm localization. So if I get there, then you'll see it's not that important, but we do get another one, you know. So another one on the list of 100,000 equivalent formulations of property A. Right. So that's it for that. Now I want to kind of go towards the more recent stuff, which then ends with some rigidity results. So yeah, so that's another story in a sense, but it has to do with quasi-locality. Because it kind of starts, again, for me, trying to find the counterexample to the statements that we had before. So basically, find the quasi-local operator on some space which is not in the row algebra. And right, so let me go back a bit to this list of things. Right, so I told you that, okay, the niceness, okay, so the niceness goes this way. And here are the sort of the bad things, right? And you can kind of tell, right? So I said, well, the first theorem is we assume something of that sort and we get some result. And then we generalize this to assume just that and get some, you know, basically the same result. So you can, well, you know, so that the instinct is, well, if I want to find a counterexample, I should start looking there. And the thing is I told you back when I was looking at this slide, there isn't that much stuff that you can try there actually. So the kind of bad examples in this business come from expanders in some way. So I'll explain what an expander is in case you haven't seen this before. So first, bunch of notation and terminology. So if you have a finite graph G, I will write dx for the degree of the vertex x. So how many edges go out of it. I will write this x tilde y for two vertices x and y if they are connected by an edge. And then here's a sort of a matrix. So an operator in B of L2 of Gn, which is finite dimensional vector space. I will use the notation delta sub G. Yes, I'm trying to define a graph Laplacian. So it's a finite matrix which you can write a formula for. It looks like this. Now, if the graph is regular, meaning that all the d sub x are the same number, say d, then this is really nothing else than sort of 1 minus 1 over d times the adjacency matrix. Okay, so it's just a matrix which just kind of encodes the graph in a sense. And it's analogous to actual Laplacian, right? So it's if you look at the formula, what it's doing is, well, at the point, I mean, if you apply it to a function and look at the value at the point x, what it does is it takes that value of the function and then subtracts somehow the average of the surrounding values, right? So like a Laplacian should do, right? It has propagation 1 because it only cares about the values of the vector at the point and then at the surrounding things distance 1 from it. So if you write the matrix, it's propagation 1, and it's a positive operator. It has so if the graph is connected, well, actually in any case, 0 is always an eigenvalue of this. So if you take a constant function on the graph, well, okay, let's say if the graph is regular, then the constant function is in the eigenvector for the eigenvalue 0 for this guy. If the graph is not regular, then you kind of have to fiddle with the degrees in a sense, right? But it's just yeah. But it's a positive operator. It's a finite dimensional space, so there is some gap, and then there is the next eigenvalue, which is now a positive number, and let's denote that one by lambda sub g. Right. So definition of an expander for a function analyst is this one. So a sequence of connected finite graphs is called an expander if the following 3 conditions. So this is the second one. So the first one is that the degrees of all the graphs, the degree of all vertices in all graphs should be uniformly bounded by some number, right? The second condition is that the graph should get larger and larger as we go to infinity. So that's the second condition. And the third one, this is the most tricky one, which is that if you, for each graph, we consider the smallest non-zero eigenvalue of the graph Laplacian, and we require that all these guys, for all these graphs, are uniformly bounded from below by a positive number, right? So maybe I shouldn't really do a spiel for expanders, but I mean, the main, again, if it's the first time you see these things, which you probably don't if I look at the list of participants, but in any case, highly connected graphs, right? So highly connectedness comes from this thing. And it plays against, I mean, of course, you can make graphs connected by adding one bunch of more edges, right? And so this is kind of, push and pull with the first condition where we require the degrees of the vertices to be uniformly bounded. So that kind of puts a bound on how many edges you can just sort of randomly put in. But then the eigenvalue thing kind of tries to make the graph as connected as possible. So this was, eigenvalues and things. So function analytic version of the definition, but there's also just the graph theoretic version of the definition where I replaced this last condition with the following thing, which I'm going to read because I'm going to come back to this again in a bit. So this is this Chigger constant thing. So let's go from the inside. I want to look at numbers like that. So if I take a subset of one of the graphs, which is, well, it's not an empty set, but it's also not too big. So it's less than half the graph. I want to compare how big its boundary is compared to the set itself, right? So by size, I really just mean it's all finite things. So I just count number of points. So the vertical bars is number of points. And I compare the number of points in the boundary with the number of points in the set A. Now the boundary of a set A is, well, all the points distance, well, it's graphs, so I can talk about edges, right? So it's all the vertices which are not in the set A, but are connected by an edge to something in A. So that's the boundary, right? So I mean outer vertex boundary, if you want. So I look at all these numbers for all the subsets of all my graphs, which are not more than half the graph. and I look at, well, I take the infimum of all those numbers and I can require them, that infimum, to be greater than 0. So that turns out to be equivalent to requiring this infimum of the eigenvalue stuff. Okay, so I mean, the Chigger, so the name for this, if you want to Google this, this is like a Chigger constant for a single graph. And there is an inequality between that number and, I mean, both way inequality with some function of the eigenvalue, right? So this version is sort of geometric, like you just look at the graph, look at some subsets and some boundaries and things. And this is sort of, yeah, linear algebra. Here, but on the scale of things, on this chart, here be dragons, expanders live here. So they do not coarsely embed into any of the stuff, so they do not have any of the other nice properties. Right. Okay, so how does, I mean, can we use this somehow to get some interesting elements, interesting operators on somewhere in some row algebra, or not in the row algebra, right? So the classical construction goes on like this. So connected and again finite graph denote the spectral projection of lambda g corresponding to the eigenvalue 0 by p sub g. So this is just notation, right? If it's a finite graph and it's a positive operator, the spectrum is a subset of 0 to norm of lambda g, sorry, delta g. So now I look at the eigenvalue 0, which I said is always an eigenvalue, and I denote the spectral projection by pg, p sub g. Right, and I here say I project onto constant function. For that, I need to add the assumption regular graph, and again, just means every vertex has the same number of neighbors, and then this pg will project onto constant functions. And it's, I mean, we call it averaging projection because it really, what it does, if you look at the formula, the projection really just literally takes a vector, a function on the vertices, and replaces it by a constant function equal to the average of the values of the function. So that's why averaging projection. And if you write down its matrix, it's a matrix something like this: 1 over n, 1 over n. Everything is 1 over n, where n is size of the space. I hope I may be missing some square roots somewhere. But anyway, it's a matrix like this. No, I think it's fine. Yeah, this should be all right. Thank you. Right. Now, okay, so what next? So let's take a sequence of connected graphs now and consider this coarse disjoint union, right? This is why I was banging on about this at the beginning, because now that's my space. So my space is now like a, well, disjoint union of a bunch of graphs which are getting further and further apart. Then, I mean, for each individual graph, this delta sub gn is propagation 1 in the metric on the finite graph. And so if I take the direct sum, that's going to be like a propagation 1 operator on any LP of x. And I mean, it's going to look like this, right? So it's going to be this block diagonal where the blocks correspond to the pieces, the individual graphs, right? So it belongs to it's propagation 1, it belongs to the row algebra. So now I switch to just talking about sister algebras. So why not? So it belongs to the uniform row algebra, sister algebra of x. Now, the thing is with this expander assumption, remember, right? So the assumption of being an expander is that each of these guys has a spectral gap around 0, which is sort of uniformly bounded from below. And so that tells you that the sole operator has 0 in the spectrum, and then there is a gap, and then there is some stuff, right? And that means that you can apply continuous functional calculus and get the spectral projection corresponding to 0 for this whole direct sum guy. And that's going to live in the same sister algebra as this operator, the direct sum, right? So if the sequence of graph was an expander, then this direct sum of the spectral projections is going to again belong to the row algebra of x. Okay, so this is where the expanderness, I mean, this is pretty much the main thing why expanders are so discussed in this business, is because this argument works in a sense. And not just that, I mean, what the element that you're getting, this P, which is direct sum of blocks like this, right? So this is, for each block, it looks like that. And now, but the resulting guy is like a huge matrix where you have individual blocks which look like that. And I mean, there's something weird about that operator, namely that it obviously does not have finite propagation, because every block is filled with numbers. I mean, they're getting smaller, but it's all filled. So it does not have finite propagation. It does belong to the row algebra. And yeah, so it's something that's called referred to as a ghost projection. So it's a projection because it's a spectral projection, and the ghost property refers to the fact that the matrix coefficients actually go to 0. Okay, now that wouldn't be, I mean, there's a whole bunch of these things in any row algebra, namely all the compacts, well, finite rank operators and all the compacts are like that, right? But the point is that this is a non-compact projection because it's a rank 1 projection in each block. And it's a direct sum of these things. So it's an infinite rank projection, which is a ghost. It's because it's infinite rank, it's not compact, and it still does belong to the row algebra. And these things are weird. I mean, these have sort of weird function analytic properties. And these are sort of used to get counterexamples to the Coarse-Baum-Kohn conjecture in some sense, right? So these are the guys which give you K-theory elements, which are not in the image of the assembly map, if you know what I'm talking about. If you don't, then anyway, they kind of, this is the route to get some counterexamples to the Coarse-Baum-Kohn. So, okay, so of course I thought, well, I have what, 2 minutes, right? So of course I thought, well, let's go with these. Let's try if I can, I mean, these are weird things. So let's see if we can cook up this counterexample to my question, well, to the question I was trying to answer. Namely, can we get one of these guys? I mean, can we get a space where this guy is quasi-local, but it's not in the uniform row algebra? Well, you know, expanders don't quite work because for expanders, this guy is actually in the row algebra. But I thought, you know, let's try to cook up some space that would do this. Turns out impossible, not a good thing. But along the way, we discovered the geometric condition. So here we go. The statement is like this. This projection P is quasi-local if and only if X is what we call an asymptotic expander. And this is really, really terrible terminology. I apologize for all of us. But yeah, so this was in the paper with Piotr Nowak, Kang Lee, and J Zhang. Okay, I'll explain what that is in a bit. And turns out that's actually equivalent to P being in the row algebra. So that's another paper where I'm not on. So I'm not on this work. It's by Anna Chuchro, Kang Lee, Federico Vigolo, and J Zhang. So there is an intersection, but yeah. So it turns out this guy is quasi-local if and only if it's in the row algebra. So it does not provide a counterexample to what I wanted. But we discovered kind of another geometric property, which we call an asymptotic expander. Now, thing is, right, so this is this game that is played a lot in this, right? So you kind of play the coarse geometric conditions on a space versus some kind of function analytic things in the row algebra or about some operators. And so this is one of those, right? So we characterize analytic condition, namely that this operator P is quasi-local with some geometric one, which is this one. It's sort of like being an expander. So we again try to look at the minimum of the size of the boundary to the set, so this ratio. But now we don't. Now we only look at. So the condition is that for any alpha between 0 and a half, we only look at sets which are at least alpha proportion of the set, and at most a half, as before, right? And so for each alpha, we require this infimum to be positive. So it's more general than being an expander, because if you're an expander, then you satisfy this. I mean, even you can even inf over alphas, and you still get something positive. But this time around, as alpha goes to 0, you can get, you know, smaller and smaller lower bounds on the isoperimetric bounds, like on this. Right. Okay, and the newest paper is doing a measured version of this. So let me ignore the measured condition. Let me just say, so here we looked at a particular operator, which was, I mean, you can write this guy down without even talking about the row algebras at all, right? You just take, coarse-disjoint union of finite graphs, and you write a matrix, which is block diagonal, and each block you have this averaging projection with just the same numbers in. So
Can
then the next, yep.
Yeah. What do we know about embeddability of asymptotic expanders? Does he, for instance, embeddability into L2 or NAP?
Right, we have a result about this. I'll get there. Yeah, cheers,
Okay.
Thanks. Yes. But yeah, the answer is no, they're not embeddable into anything. So yeah, just like expanders. So we have, okay, let me get back on track. Right, so we talked about this operator P. So the next bit of the story is, well, we consider operators like this, where it's still block diagonal. It's still a rank 1 projection on every block, but now arbitrary rank 1 projection. Right, so instead of just doing this averaging thing, you actually, you allow any rank 1 thing. And so that then leads to a measured version. So instead of counting points, you kind of have measures on all the pieces, and the story is more or less the same. And the story is more or less the same in the sense that I still don't get my highly sought after counterexample, because it turns out the same theorem as on the last page holds. So S is quasi-local. So any of these guys, if and only if X is this measured asymptotic expander. So we have the geometric version, but if and only if the operator is in the uniform row algebra. Okay, so yeah. And now let me just sort of state these rigidity results. So in some sense, okay, how much time do I have? So it's probably going to take a few minutes.
In general, the seminar is about an hour, so can keep on going.
Okay, thanks. Yeah. So let me go through this, yes. So at this point, we connect with the rigidity of row algebras. So this comes back to the, okay, so what is that? Well, those are results of the sort, something happens with the sister algebras, or the LP versions of these things, and that would imply something about the spaces, right? So by something happens, I really mean some kind of isomorphism, or at least like a kind of a map or something like that. I mean, the first version was what I stated when I defined row algebras. So when the sister algebras are isomorphic, then the spaces are closely equivalent, right? So those are the kind of results that talk about the rigidity, that we call rigidity of row algebras results. And again, in general, this is not really resolved. So usually they require, to get anything, you require something, some niceness about the spaces, X, or Y. Usually just one is now enough, so X. So this was the result I had there before with Rufus, the old one, where we assume that one of the spaces is property A, and we ask that the algebras are stably isomorphic, and that would imply that the spaces are coarsely equivalent. And so these days, there are much, much better versions of this. So there's a bunch of names. So you may recognize some of them. And I mean, they get better versions of this in a few ways. So one is that they get stronger conclusion. So for example, instead of just having a coarse equivalence, they get bijective coarse equivalence. So you actually match up the point. There are now results apparently for more general X, so not just metric space, but coarse spaces. I mean, not in general, you have to assume something about the coarse structure, but in a sense, much more general than the metric space. Now these guys are really, really good. They get even embeddings versions. So they assume that there is a map this way. You need to assume more than just a star homomorphism. It has to be a little more, but then you actually do get like a coarse map in going one way. So, and I mean, the main thing is that they weaken this assumption of property A to coarse embeddability into L2. Or actually what they did is they have a, technical condition, which is, well, I just say technical because it does involve, I mean, it's not a geometric one. It requires, it's some question about some operators. But yeah, so, I mean, in particular, it is implied by this coarse embeddability into L2.
I feel like I should just say that the bijective thing in the isomorphism started with Rufus and White, actually. And I didn't see their names there, so that's why I'm just...
Oh, yeah, okay, sure, yes, sorry. So...
And sorry, since my name was there, I felt like I should say it. That's the only reason I'm interrupting. I'm sorry for that.
Sorry, I should have just done that. Yeah, sorry, I'm not doing Rufus enough justice in this talk, I don't think. Yes. Okay, so what we have is this. So basically, the geometric notion we've discovered, this measured asymptotic expander. So I mean, there's an extra adjective, ghostly. Anyway, ghostly measured asymptotic expanders. So it turns out that if X does not coarsely contain a ghostly measured asymptotic expander, then we get this rigidity result, right? That if the algebras are stably isomorphic, then the spaces are coarsely equivalent. So now the question is if this weakens, I mean, if this is in any way better than the coarse embeddability into L2. And, you know, to answer the question, we do prove that, we do show the usual arguments. You can kind of use them to show that if something is a ghostly measured asymptotic expander, then it does not embed into any LP. And hence you get this corollary that if X actually coarsely embeds into any LP, you also get this rigidity result. Now I should say, it may sound fancy, but it's really just an epsilon improvement over the existing proofs. I will not try to figure out what the names are. It's the subsets of the names on the previous slide. Because we basically just show that this being a ghostly measured, not coarsely containing a ghostly measured asymptotic expander implies their technical condition in some sense. I mean, there is a little bit of an improvement, but it's really minimal. So that's how we go, right? So in a sense. So the technical condition is that no sparse subspaces yield non-compact ghost projections. So yes, I will not try to. Yeah. So it is a bit better in that this condition actually does cover pretty much all the, I mean, you know, here be dragons, this area where the things do not really embed into anywhere and are weird. We had expanders, and apart from expanders, there is really very, very few examples of those, of sort of families of graphs being there or spaces being there. And the only ones are pretty much, well, the ones I know are by Arjantseva and Teixeira and by Delaby and Juchro. So those are examples which do not coarsely, I mean, they are purposefully constructed, so they do not coarsely embed into anything. I mean, any LP. Or, well, they constructed L2, but it works for any LP. But they do not actually contain expanders in any sensible way. Yeah, so they, right, so they do not exactly, so they do not plug into the corollary, right? They do not coarsely embed into any LP. But we do show that they satisfy the assumption here. So we do show that they do not coarsely contain even a ghostly measured asymptotic expander. So again, just improving their proofs they have, we show that, you know, you play with this a bit, and instead of just not containing an expander, you get that it doesn't contain any ghostly measured asymptotic expander. And I'm really, really sorry about the terminology. It's horrible. But hopefully it's not that important, so it shouldn't really catch on. So that's good. Right. And I'm over time, so I'll stop here. Yeah, so feel anybody. So this should be the end of the talk. I'm happy to discuss other stuff and sort of stay on if you're interested. So.
Okay, thanks. Thank you very much for the very nice talk. Okay, so just one thing I think I want to say before opening to questions is that if you're apologizing so much for asymptotic expanders, then I feel very bad for saying sparse subspaces in only compact ghost projections. But, okay.
No, I disagree, because that one actually makes sense, right? If you know what these things mean, then it makes perfect sense, whereas asymptotic expander is just confusing everybody.
Okay, so do we have any questions to Jan?
I had a question. I think it's a little skewed to your interest, but when you define, could you go back to the slide on quasi-locality really early in the talk?
Yep.
Yeah, so yes, exactly. And so so for finite propagation, you have this chi-A and chi-B on the left and right, and you're asking with 0. And so another thing that we do with these a lot is I'll hand you the chi-B, and I'll say, can you tell me what's the smallest chi-A that preserves that? Like, what's the left support of T chi-B? And so the image is sort of like you have a graph, and you're like specifying here's B, and then you're sort of finding the cross section across the A. I don't know if this is making sense.
So, right, it does.
Or like you could ask, what's the biggest chi-A that makes that 0, and then take its complement or something. Is there any notion of this for the quasi-locality? It seems like there wouldn't be, but
so yeah, I haven't seen this in this connection, right? I mean, if so, kind of spiritual. So you are sort of asking for. I mean, this is sort of like trying to estimate the propagation, but not sort of everywhere, but like at a specific place, right? In a sense.
Right.
So if you buy into this then the propagation is, I mean, having a finite propagation guy, you are requiring that the interaction that the matrix represents really happens at a fixed scale. And so you're asking for a kind of a local version of this. I have not really seen this used in any kind of way. So I'm not sure. I'm probably not really helpful at all. So
it seems unlikely, but it also seems like it would be useful. So I don't know.
Yeah. Could be. Might very well be.
An essential
yes.
support or something.
Yes.
Right, well, thank you.
Also, it seems like you could do this for course structures without a metric. You just need to say that for every epsilon, there's an entourage in the that belongs to the course structure, so that if A cross B misses the entourage, then it's less than epsilon. That's not a problem.
Yeah, so certainly all the finite propagation Roe algebra business, I mean, that works for course structures, as you say, right? You just kind of, instead of, I mean, the R, you have the entourage, and it all kind of works. So I assume that you can define this. I'm not sure. So I have not really seen this studied actually, but yeah, I mean, it's a good question.
I'm sort of wondering about this asymptotic expander thing.
Okay.
You know, somehow, I don't know, naively, like an expander, I mean, one of the first examples I saw of expanders was just sort of say coming from like a residually finite property T group. And that is because you can relate this Cheeger constant to, you know, this uniform bound on the Markov operator. Can you say something like that for asymptotic expanders? Can you say there's some source of them coming from some weakened version of property T or something like this? Or
yeah, so that's going to be a bad news on this in a sense. So that's why I'm happy it doesn't catch on. So the way they prove this, they prove this last bit here. I mean, Anna Kukuro, Kang, and Federico, and they basically prove a structure theorem about asymptotic expanders. And it turns out they aren't too far away from expanders. So first of all, if the graphs are in any way regular, sorry, I said, no, again, I use regular in a different way. By regular here, I mean, say, vertex transitive or something like that, right? So for every 2 vertices, you have like an automorphism of the graph. Then an asymptotic expander like this is actually always an expander. So if you're thinking of constructing these guys as sort of the, this sequence of quotients of some group, and it's either an expander or it's not even an asymptotic expander. Okay. So let me give you an example how this guy looks like, and then basically tell you all of them look like that. So you take an expander, an actual expander, and then you take another family of graphs, which is pretty much anything, but it's sort of in size smaller than that, right? So you tack on a small graph here, maybe a big graph here, but something like that. And as long as you keep the ratios of the expander part and non-expander part going to 0, what you get is an asymptotic expander. Right. Okay. So you can imagine just stacking on either like a line or a circle. I mean, actually, literally like a cycle, larger and larger size. That kills the expanderness, of course, because I mean, in that part you have sets with small boundaries. But somehow this alpha stuff allows you to, I mean, it kind of, I mean, the condition then in the end, I mean, in the limit only really looks at the expander part in a sense, right? Because, right, so if you fix the ratio and the pieces are getting smaller and smaller in proportion to the whole bit, then eventually you aren't allowed to take any of the subset of the smaller attached bit. Like any A that you can consider actually has to contain like expander part. Mm-hmm. And then you use the expander condition for that part, right? So anyway, this is an asymptotic expander, and they prove basically a structure theorem like this. So they prove that any asymptotic expander, you have, well, maybe not just two, but there may be, you know, sort of infinitely many portions of the graphs. But if you sort of look at one fixed family, it's actually an expander, right? So it's, in a sense, it tells you that the structure of these asymptotic expanders isn't that interesting at all. So because they are just kind of come from expanders and then you tack on some stuff.
It kind of reminds me of, you know, if you're familiar at all with sort of like sophicity of groups or something, you can modify this residual finite approximation to create some other sequence of graphs, which most of the times looks like your Cayley graph, but not always. And there's a classification of what kind of graphs you would get if you took a property T group due to Gabor-Kuhn, and my guess is it just says that they're all asymptotic expanders, but that wasn't a term that was introduced yet.
Okay, yeah, that's a great suggestion actually. So yeah, thanks.
Yeah, because it seems to say a similar thing where you take this graph that you get, and because you're allowing some error in where it looks like the Cayley graph, you can't say that because it's a property T group, it's literally an expander. But if you just take the same vertex set, delete and change a small number of edges, then it is. So
yeah, that's actually, yeah, thanks. This is extremely useful. So that's a really good question, whether you can connect. I mean, whether it's possible to connect this with with sophicity. That's great. Thank you.
Yeah.
Do we have any other questions?
Maybe just a comment or, well, to clarify for myself. You have this, your theorem at the end said something like that if you don't coarsely embed in L2, for example, then you have none of these measured expanders and therefore same conclusion, you satisfy the technical condition, which if you just use L2, that's in the work of the people with these initials, rather Ferrara, I guess, in that case. But in their case, it goes via some complicated K-theoretic arguments to say that the sparse subspaces with non-compact ghost projections can't exist. Whereas in your case, it seems like it's much more direct. That's correct, right? You're not going via.
Yep, it's pretty simple, really. It's basically what I had before, right? So take a sparse subspace. If it is a measured asymptotic expander, that means you have one of these. I mean, that's equivalent for that operator. So that you know, the block rank 1 guy being quasi-local, that's equivalent to it being in the Roe algebra. And there you go. Yeah. There you have a ghost. Ghost. I mean, right. Oh. So it is really direct here, in a sense. Yes. And and basically, because we have the geometric version, we get all the LPs kind of for free without having to do any Banach business, right? Because the LP version for us, I mean, on the geometric side, you don't see the LP, right? It's just that they don't embed into an LP. So.
Thanks.
Yeah. Thanks. Yes. So this is really, that's why I say it's a small improvement, because it's literally just that, right? It's just that argument. I mean, you have to fiddle, but
it's a small improvement in terms of the level of generality of the result, but the fact that the proof is more direct is good.
Yes. Yeah. Of course. Yeah. But yeah. I mean, because I just say because we literally just plug into the technical condition.
Yeah.
It's just that we kind of got lucky and we ended up having a nice geometric characterization of these block rank 1 guys existing in the Roe algebra. Yeah. So I mean, the improvement is we only actually get that they don't yield any non-compact block rank 1 ghost projections, because that's the ones we deal with. But it's enough to get the full, I mean, to get the result. So, I mean, I must say I was pleasantly surprised that we could, well, Kang with Javan could show that these examples of Gulnaras and Romans and Anna do satisfy this. But again, it's not, we don't really do any new thing, right? We use their argument and just show that it goes through when we do this measured version of this. So.
Can you say anything, by the way? Sorry, I'll probably stop asking questions in a minute, so I'm taking time. But can you say anything? It's block rank 1. Can you say anything for more general block ranks? So, like, I mean, you get more complicated ghost projections coming from property T, for example, with higher ranks. Is there a geometric condition underlying that?
I did not think about that at all, I must say. So. Yeah, I mean, I must say, I was even skeptical about this block rank 1 version, but Joanne kept badging me about it, and so we ended up doing something. Thing is, right, so if you have a block rank 1 guy, then on each block, it's a rank 1 guy, so it's like, you know, an inner product against the vector. And then this vector gives you the measure on the thing. Yeah. Right, so in some sense, that's the connection. Why do we do this measured business? Because, right, I mean, before, for the averaging projection, this was just a constant function. And so that means that it's the normal counting measure, and then there we go. In general, if it's rank 1, we get this. Now, more generally, you know, you kind of have to probably come up with a better sort of space, kind of structure on the space, which would somehow play with the form of the operator, right?
Right.
So I must say I didn't really think about this before. So yeah, thanks. That's a useful one.
So I have a question. So I took a look at your paper on this quasi-locality thing with Zhang, and if I'm not mistaken, you guys use the characterization of property you guys use is actually not one of the ones you mentioned, I think, there in the slide.
Yeah, we use, like, I mean, it's used, I think, twice at least.
Okay.
So this is the rest of my slides, basically. So if you want, I mean, I would recommend stopping the recording, or, you know, letting people leave if they want. And I can kind of explain how does the argument go, if you like. So.
I mean, I would definitely be up for staying a bit longer. I could stop the recording and keep on going. So okay, so we can follow your. I would be happy to follow your advice, your suggestion. So let me stop then the recording.